Welcome back. Today we're talking about shear acceleration. This is what I've been working towards for the last 9 or so videos. So I'm going to start with a mechanical pencil. Hopefully you can see it better than in the other videos. I don't have a compass handy to make a circle. Alright, there is the globe Earth. That'd be a radii, the radius. Again, I'm using rough numbers. 4,000 miles in our case. It rotates about an axis. I'm not going to show the tilt. There's no reason for that in this description. It rotates this way. And we talked about somebody standing at the North Pole who simply rotates once every 24 hours. That would be a very boring ride on the playground. And then we talked about this fellow. This is how much do I weigh at the equator? And we saw that the force attributed to gravity pulling him inward, and the effect, the centrifugal effect pulling him outward, are both in the same line, opposite each other, and so they cancel each other out. And we showed that this one is about 0.3%. So the difference between 200 pounds at the pole and 200 pounds at the equator was 2/3 of a pound. So we'll say that this is off by about 1/3%. No motion, there's no way you could feel it or detect it. No large motion, 1,000 miles per hour linear speed, but still, when in comparison is something like 390 times smaller than the weight that we would feel based on gravity. So we've done at the pole, that'd be 90 degrees north. We've done at the equator, which would be 0 degrees. And now we get to do home, 45 degrees. So again, there's a man standing there. Can he feel anything? So the gravitational pull will be the same as before. In our case, I'm using feet per second squared for the acceleration due to gravity. So all these are indiscernibly the same. However, when the Earth rotates this way, the radius, I'll draw the axis of rotation. The radius that he is spinning around at is this piece of a triangle here. And so the centrifugal effect will be pulling him off in this direction. And because of the rules of the free body diagram, where we treat the entire person or the entire object as a point mass, it doesn't matter if I draw this arrow, this vector, connecting to the tail of gravity or off his head. It doesn't matter. It's going to be the same. So quickly, a little bit of math. The radius is 4,000 miles. The angle is 45 degrees. And we need to know this opposite side, which, if it's a 45, this one's also 45, which means that these two sides are the same length. We'll call them R. And in a 45, 90 triangle, R squared plus R squared equals 4,000 squared. Two R squared is 4,000 squared. R squared, 4,000 squared divided by 2. $4,000 squared divided by 2. And then we square root both sides. So R is equal to plus or minus the square root of 8 million. So R is equal to 2828 miles. So the radius, or the length of the string that this person is on that is spinning around in this direction, is not the 4,000 miles. It is shorter, which will reduce the centrifugal effect. However, it is not nullified or canceled out by gravity. So we could also find this side by doing trigonometry. This would be sine 45, would be this side divided by that side. So 4,000 sine 45 will also give us the 2828. All right, so if the radius is 2828, the next we need is the circumference. And the circumference is 2 pi r. I conveniently have it already here, times 2 times pi. Circumference 17771, or I could round up. The radius is 28, quite a bit less than 4,000. The circumference is 17,000, quite a bit less than the 25,000 we've seen before. What else we need for centripetal acceleration is we're going to need the velocity. And the velocity is equal to the circumference divided by the time it takes to do it. Well, it turns one rotation, it turns 17,771 miles in 24 hours. That gives us 17,771. Too many sevens. Miles over 24 hours. 740.5 miles per hour. Okay. We have the radius. We have the circumference. We have the velocity. And the centripetal acceleration is equal to v squared over r, which in our case is going to be the velocity squared divided by a radius. So 740.5 squared divided by 2828. It's 193.88. I'll round up. 194. And the units on this are miles per hour squared. Well, we know that the red vector here is approximately 32 feet per second, so we need to convert this. 1 mile is equal to 5280 feet. Hour squared, 1 hour is equal to 3,600 seconds, and that conversion is squared. So we have 194 times 5280 divided by 3,600 divided by 3,600. And I get 0.07899. So I'm going to do 0.79 feet per second squared. So now we are comparing 32 feet per second to 0.79 feet per second squared. Is that enough to even concern ourselves with? I think it is. So this time I'm just going to draw this upper northern hemisphere right-hand side. A 45-degree angle. I'm guessing at drawing it, but that won't change the calculations. And at this point, the centripetal force and the centrifugal effect are going to be off at a sideways motion. Hence the word shear, sideways. So we have gravity pulling toward the center of the Earth. And we have this other acceleration off at a 45-degree angle. So what is going to happen? They're going to cancel each other out. Gravity is pulling in this direction. This vector pulls off to the right. They're going to combine and cancel. So how we add vectors is we add them up. We'll do, I'll exaggerate it so we can see what's going on. This will be gravity, 32 feet per second, and then exactly at a 45-degree angle back this way, we have this little guy, which is our 0.79. Here is the surface. And here is our blue man. And the blue man is holding in his hand a plumb line. Where's it going to hang? When we combine vectors, this is called head to tail. We go on the 32 and then we go backwards this way. And the actual net gravitational component will be this green piece. The green vector is the direction the plumb line will hang. Now, it has been exaggerated. This is not to scale. But both in length, the 32 has been shrunk up a little bit, and in direction, the 32 has been tilted over this way. So I'm going to draw the plumb line in his hand, and it is true to my drawing, to my scale. There's a plumb-bob at the bottom. Clearly not in the same direction as the center of the Earth. Clearly not in the same direction as gravity. So the question is how much? So we're going to focus on this piece down here. We're going to assume that this radial component is our level or our baseline. I'm going to draw this small triangle down here. We know this angle is 45 degrees. What we need to know, we're breaking this vector here into components. Part of it is exactly in line with the 32. We're going to call that the x component. And then there's the component that is perpendicular to the 32. We'll call that the y component. And in this case, they happen to both be the same size because it is a 45 degree triangle. We know this length, which is 0.79. From before, it's going to be root 2 over 2. Just happen to know that. So in this smaller triangle, we know the hypotenuse is 0.079 and the two other sides. So this triangle exploded over here. It's 0.05585. So round it up to 0.6. So this is our small triangle down here. So first, I'll just kind of keep drawing the same figure until it's all finished. So we've broken up the 45 degree centrifugal effect into this smaller triangle. So our gravitational component, it's going to be there. And it has been shortened. This side here is 0.056, which leaves this portion to be 32 minus that. We know this side here is the 0.056, so we can solve for the length of the red side. I'll explode it over here. So 32, take away that, is 31.944. The side down here, 0.056. The hypotenuse in this case, this squared plus this squared is equal to that squared. $31.944. So that shows us that this amount is so tiny in comparison that it almost thinks that this is an isosceles triangle. So essentially, your weight has not changed. So this guy who's trying to stand up can't do it. The plumb bob in his hand is going off at an angle like this. He essentially weighs the same. So we're not going to say the 200-pound man weighs significantly different. But that's not the important part. The important part is the angle. So we have the red side. So that would be this green side here. Next we need to find this angle. And I'm going to go back to these two sides here. This would, from this angle, this would be the opposite, this would be the adjacent, that would be tangent. I'll just say tan phi is equal to the opposite divided by the adjacent. Inverse tan this. .1004 and so on. So the angle of deflection is 0.1 degrees, which means that where I live on the 45th parallel. There's a sign on Interstate 5 just north of Salem, Oregon, and it says, "Welcome to the 45th parallel. You are halfway between equator and the North Pole." There is a line called a tangent that just touches the surface of a circle, touches at one point. In this case, I'm drawn it to show that it touches at that point. The tangent here would be what we would measure level with a spirit level or the surface of water or anything like that. So if I'm going to exaggerate it again. If the plumb bob hangs off at a significant difference, how would you know? If you put up a building and we hung a plumb bob here, and this was going to be south, and this was going to be north, and this was going to be west, and this was going to be east. If you hung a plumb bob on this side of the building, it will lean south by 0.1 degrees. If you hung the plumb bob on this side, it would hang straight down. What do you think?